Big Data, Big Impact Analysis workshop. My name is Akash Vemulapalli, and I'm the analysis lead for Big Data, Big Impact. During this workshop, we'll cover a few basic concepts from Python libraries to basic concepts behind analysis and simple machine learning models. So this is the outline of what we're going to cover during this workshop. First, we're going to talk about what even is analysis. How do we analyze data? What does that actually mean? Then we're going to look into some common Python libraries that you're going to use during your analysis. Next, let's look into some basic concepts on tools and structures you'll be using during the analysis portion of your project. This ranges from tools like Google Collaboratory to actual concepts like data preparation and data visualization and how you would do that. Next, let's look at some basic machine learning models ranging from supervised to unsupervised, and then some techniques like dimensionality reduction, clustering, perceptron, and a support vector machine. Finally, we'll take a look at some of the resources that could be helpful to you when learning more or diving deeper into these concepts. So what even is analysis? At its core, analysis is finding insights based on data. When dealing with large data sets or when trying to find insights from data, it's really important to have lots of data. And then from there, it's going to be a very hard job to find what does this data mean, what are like the hidden insights behind this data, and how do we actually analyze it to find out these secrets. Oftentimes, when doing analysis, you'll be working with Jupyter notebooks, which means the programming language you'll be using is Python. There are like built-in libraries or built-in structures for Jupyter notebooks like Jupyter Lab, but oftentimes what's most convenient is using Google Colab. Google Colab is a tool that's just used to run Jupyter notebooks online. It's very convenient for running data and for loading data and for machine learning. We'll also have to look when doing analysis to also make sure that data is prepared properly and in a good structured state for the analysis to take place. Then obviously there'll be some machine learning used when it comes to actually analyzing data and finding these core insights. So what is a Jupyter notebook? It's just a way to write and execute code via a web application. It's very simple and streamlined and lets you combine text with code. This is very important, especially when it comes to analysis, because it lets you annotate your thought process and kind of describe your model as you go. In this image below is an example of what a Jupyter notebook would look like. We'd have some text describing what we're doing, then we could have code in line with text. For example, there's some Python code to just calculate the amount of seconds in a day, which you can just do by multiplying a few numbers. And this is a good way to combine logic and annotation and kind of describing your thought process and what analysis you're doing with the actual code that executes on that. Google Colab is just a way to work with code collaboratively, and it's just a way to run Jupyter notebooks online. By using Google Colab, there's automatic access to GPUs and CPUs, which makes it very easy to run these machine learning models because oftentimes they are pretty intensive when it comes to computation. It also lets you upload your own data, oftentimes from Google Drive or from GitHub, or just by loading your own data sets in. This is really helpful because when doing these analysis jobs, we have lots of data that we need to work with, and being able to upload that and work with it natively in Google Colab makes it very easy. And then once you're done writing your entire program in Google Colab, it's possible to export all the code as a Python file, and that makes it really easy to integrate with with the core aspect of your project. For example, when I was working with Google Colab in the past, what I would do is I'd write out an entire Google Colab notebook. I'd have text describing what I was doing combined with code. And then once I know everything ran properly, then I just export it as a Python file and integrate it with the rest of my project. Whether that's working with Flask or uploading it to a database or just running more code with your Python file, that's all can be integrated once the actual analysis portion is complete. And being able to export as a Python file is just very convenient for that. And in addition, Google Colab combines Markdown and Python code together. This is pretty helpful, as I mentioned before, just for having a sane thought process when it comes to coding, to help describe your analysis and to help view visualizations and the output of your code in line. There are a lot of different libraries when it comes to analysis. Oftentimes, you'll be working with Python just because all the libraries that go into analysis and machine learning are usually coded with Python. Some of the common ones include NumPy and TensorFlow, and Pandas and Matplotlib. NumPy and Pandas are often used for handling data. When it comes to data, it's often structured in a database format with tables. And in that scenario, NumPy and Pandas work really well because of NumPy arrays and Pandas data frames. This is just a very convenient way to store data, especially multi-dimensional data, where we're not working with two features, we're working with lots of different features. Storing it in an array is just a natural way for you to map out how this data is stored. In addition, there are machine learning libraries like TensorFlow, and as we'll get into later, there's some more machine learning libraries like PyTorch and Keras which just makes it possible for you to actually run machine learning models or for you to use pre-computed and pre-coded functions and algorithms. In addition, when it comes to data visualization, it's a pretty important part of analysis. Even though the way big data and big impact structures project is to have a separate team for analysis and data visualization, you always want to make sure you're visualizing your data and visualizing your analysis throughout your coding. This is important because when dealing with these large data sets and when trying to find out whether your analysis is actually working or not, being able to visualize data, being able to plot things out with graphs, being able to find out whether your analysis is accurate or not is pretty important. And tools like Matplotlib is pretty helpful for that. There are also other visualization libraries like Plotly, but Matplotlib is pretty standard and it's pretty easy to learn. All of these different libraries may seem overwhelming at first, but there's tons of documentation online when it comes to learning how to use these libraries, when it comes to example functions, and when it comes to example projects. So with analysis, there's so much that goes into the machine learning aspect. There's so many different libraries. It's a pretty daunting and pretty large field. So a lot of this workshop will be giving you a broad overview on some of the libraries and techniques and algorithms that you may need to use. And then you will have to dive deeper into these on your own. And I'm happy to provide resources or links or any tutorials if you need more assistance. But all of these different libraries and frameworks have lots of extensive documentation online. When it comes to the actual machine learning aspect of analysis, a lot of the libraries used are like TensorFlow, like PyTorch, like Keras, and like scikit-learn. A lot of these machine learning algorithms are common across different domains. So a lot of these libraries have pre-computed functions, have neural networks built in, have optimizers, gradient descent functions, have clustering algorithms. All these algorithms are baked into these libraries. So oftentimes you rarely have to code them from scratch. It's just as simple as setting up PyTorch, setting up Keras, and saying, I want to create a neural network. This is the input data. This is what I want the output data to look like. And it's all programmatically done through the libraries. So coding things from scratch isn't really done when it comes to analysis because all of these algorithms, all of these neural networks have been optimized by these different Python libraries. So now let's dive a bit deeper into data preparation. When it comes to analysis, the first thing you want to make sure is that you have good data. Good data is essential when it comes to analysis because without good data, you're not going to be able to find good outputs, be able to find good insights, be able to find the answers you're looking for. So when it comes to data preparation or data wrangling, the really key insight and technique there is just you want to transform your data into a usable state. There's lots of different aspects that goes into that, and each one of these different bullet points can be an entire workshop by itself. But just to give yourself an idea of what we have to do to make sure that data is prepared, one of the big steps is to make sure that our data is clean. Whenever we load data sets from online or whenever we're dealing with data, there's oftentimes lots of messy data. There can be outliers, there can be null values, there can be zero values. We can deal with delimiters. It's like if you're importing things into a CSV file and there are commas in the data, that will mess things up. So we just want to make sure our data is clean and as clean as possible. And there are a few different techniques here, which we'll dive deeper into later. Next, we want to look into feature selection. This is really important when dealing with very large data sets, and especially when we're going to target a subsection of that data set. We want to make sure we choose the most relevant data and the most relevant features, because otherwise we have lots of irrelevant data, which ends up influencing our model and influencing our code. This is just boils down to just choosing the most relevant data, which may seem simple, but there's a lot that goes into knowing what data is actually important when it comes to a machine learning model, what data is useless, what data is important, what data will actually result in good conclusions, and what data will mess things up. There's no way to really know that beforehand. So that's a pretty important idea when it comes to analysis. You want to make sure you select what columns in the data, what features in the data are actually important. Another important idea when it comes to features is feature scaling. Oftentimes when we load in data sets and we're dealing with large amounts of data, there are outliers. And this makes things very complicated, especially when these outliers can range from millions of values to like very, very small values. And this can lead to problems when it comes to the mathematical computation behind all of these algorithms. For example, if we're multiplying lots of really, really small values together, like we often do in neural networks, this can lead to values being really, really small. It can lead to inefficient computation. It could lead to things timing out. It can lead to the computer automatically rounding things down to zero. So one key idea here is feature scaling, is we want to bound values between a certain range just to make things standardized. When we're dealing with values ranging from like 0 to like billions and trillions, We just want to divide things down, maybe make things a ratio between the smallest and the largest value. And then once we actually compute our analysis, we can scale things back up to the original value. So that's just the basic idea behind feature scaling. Feature engineering is probably one of the biggest and most important ideas when it comes to data preparation. And this is essentially is just deriving new features from existing data. Oftentimes, we have data sets with data and different columns and different conclusions. We want to make more data from our existing data. Some examples I pointed out here are changing stuff from like a timestamp, from like a Unix timestamp in milliseconds to like date or a time. Or if you want to change things for like a stock model from an open price to a closed price, we can make new columns, we can make new features just by doing some basic operations. For example, if you have an open price and a closed price, we can just subtract the two and then divide it by the time to get a percent change. And this is a pretty simple feature engineering idea, but things can really ramp up. When it comes to feature engineering, we can do lots of different things. We can combine data together. We can run new data sets. We can run new analysis tools just to get more features. We can also run machine learning models on subsets of our data to get new insights, new data. So feature engineering is like a really big field just by itself. In addition, data augmentation sounds very similar to feature engineering, but they're two separate ideas. Feature engineering is just making new features from existing data, but data augmentation kind of encapsulates that and has some more ideas. For example, when you're dealing with machine learning libraries and when you're trying to use machine learning or use neural networks, it's really important to have lots of data. And oftentimes, if we don't have lots of data, there are a few tricks we can do to augment our existing data set. For example, if we're doing some sort of convolutional neural network and we're dealing with some computer vision project, and we don't have enough data, some techniques or some computer vision textbooks suggest duplicating images, adding noise, or adding synthetic data to your data set just to artificially influence it with more data. It turns out these techniques actually lead to better results, even though we're kind of fabricating data. So data augmentation is just a form of creating data from a limited data set. You could rotate images, you could add noise to images, you can just take the average of a bunch of data and just make a new data point based on the average. That's a form of data augmentation. So data cleaning, as mentioned before, is a pretty important idea when it comes to machine learning. One key insight here is that if you put in garbage data into your model, you're going to get garbage data as your output. You want to make sure your data is organized and clean and actually has a purpose when it comes to your analysis. So as I mentioned before, there could be typos, there could be missing data. Units is a pretty big stumbling block when it comes to data cleaning. Some data could be in terms of miles when you want to convert it to feet. Some data might be in terms of hours when you want to convert it to seconds. Just making sure the units are standardized throughout your data set is really important. Abbreviations when it comes to natural language processing could lead to problems. There are different words which could refer to the same thing. For example, we could have one data entry which is NASA and one that says National Aerospace Space Agency. And this could lead to issues when it comes to analysis just because the computer has no idea what an abbreviation really means. Duplicate data is also a really big problem. White space and delimiters also lead to issues, especially when you're doing some form of natural language processing or when you're working with specific file types. CSV files especially, you want to make sure you don't have commas when it comes to the names, when it comes to features and data, because that will really mess things up. There are a few tools we can use to make sure data is actually clean. So one big tool is Data Wrangler, which is a Stanford project, just a way to work with data and work with large data sets and make things efficient. OpenRefine is originally a project, I think, run by Google, and it became its own nonprofit type of own organization. But it's just a way to work with data, deal with null values. Both of these tools, if you go to the links, they have a way to download these software and then use it for data sets. It can be really useful, especially when it comes to dealing with null values, selecting tons of data, especially dealing with large data sets. It has efficient ways to clean things up. Oftentimes, when you're dealing with data and data sets, they're in a tabular format. This just means they're in kind of like what you'd imagine an Excel spreadsheet to look like, a database. It'd be columns and rows, and each column and row pair and each cell in that kind of spreadsheet is filled with data. It's just what you'd imagine a database or an Excel spreadsheet or Google Sheets or any form of tabular data would look like. However, there are some cases where you'll deal with non-relational data. And this can be something where there's more complication. It makes it a bit harder, especially because lots of Python libraries like NumPy, like pandas, when they deal with data, they deal with it in an array format, which naturally does look like an Excel spreadsheet. It naturally does look like a table. However, if we want to deal and work with data when it comes to non-relational format, uh, there could be things like NoSQL databases. There could be things like key value pairs, and it's just something to keep in mind when dealing with data. In a tidy data set, we want each variable to be its own column and each kind of observation to be its own row. So what it would look like is we'd have values like entry one, entry two, entry three, and we'd have data like height, weight, BMI, and we just have a way to keep things in a tabular format where each row refers to a specific entry in the data set and each column refers to what we call a feature. Feature selection, as I mentioned before, is a pretty important idea when it comes to analysis. We just want to make sure that we have and that we remove features that aren't important. For example, our dataset could have a ton of features, but some of the features aren't relevant. Some of the features could lead to subpar results. Some of the features are contradictory or conflicting. So we just cut things down and deal with a smaller subset of the final features. There are a lot of benefits of feature selection. Uh, in this in this image, we can see a few of them. One of the big ones is it saves a lot of time when it comes to training models and leads to better performance. By selecting the relevant features, we make sure that our analysis techniques, our analysis algorithms don't have to go through and do the heavy work of deciding whether or not this feature is important, because we can pre-compute that, and the human mind, it just has a better idea of knowing whether or not this feature is relevant or not. And it just makes it much easier to debug models, to create models, and to interpret models when we're only dealing with less features and the features that are actually relevant to the task at hand. So as I mentioned before, feature scaling is pretty important. It's a pretty broad idea right now that feature scaling is important, but in later workshops, we'll go more into depth on why it actually matters. Just as a taste, gradient descent is a pretty big algorithm when it comes to machine learning. It's a way to optimize things and find, let's say, an optimal feature. It's a way to find an optimal parameter. It's a way to actually fine tune our model and train it. And when we have non-normalized features, it can lead to a lot of fluctuation when it comes to the optimization path. So we'll dive deeper into gradient descent later. Just know that normalizing features is really important when it comes to making sure that things run efficiently. Data visualization is also really important. As mentioned before, data visualization is kind of thought of as a separate part of the project. But when you're analyzing data, it's really important to visualize the intermediate steps, to visualize the output of your analysis, because when you see a bunch of integers, when you see like these huge sheets of text data, when you see like these arrays of data, it's really hard to know what this number actually represents. And plotting things out using libraries like matplotlib, using Python's built-in graph libraries, it's really important and it's really crucial because you can actually see and visualize what is my algorithm actually doing? Is my analysis effective? So we just want to make sure that we visualize results with charts, graphs, and plots during our analysis just to see that is things working as expected? Are there problems with our analysis? And that's it's so much easier to know whether or not there's problems with your analysis during the analysis portion if you plot things out. For example, this is an example of k-means, which is a clustering algorithm. And we can see that when we visualize this data, we see that, oh, this kind of makes sense. This like matches up with what I imagine the data to cluster as. So I know I'm on the right path. In addition, when we're dealing with neural networks or like any type of machine learning tool, we want to graph our loss and make sure that, hey, as time moves on, as we're running more and more iterations, the error in our program is decreasing, which is a good sign. So we just want to make sure to keep track of that when it comes to our analysis models. So now let's dive deeper into some of the basic concepts behind machine learning. This is kind of going to be a surface level overview of some of these concepts. We're not going to dive too deep into mathematics behind all these different techniques, just because that will lead to a lot more time, a lot more effort. And if you're curious about any of the underlying math, underlying information, or you just want to learn more in general, feel free to reach out to me. I'll make sure to send you any resources or send you any information to make sure that you learn more about how these techniques actually work behind the scenes. But in a nutshell, machine learning is just training a model on data to make useful predictions when we're given new data. And the reason why machine learning is so powerful and the reason why it's such a big buzzword is that because it lets us make predictions about previously unseen data. We can look at some data and then learn something about something we've never seen before. And this is really powerful because of all of the possibilities it unlocks. So when we talk about machine learning, there are a few broad overarching subfields. One of this is supervised learning, the other is unsupervised, and the final one is reinforcement learning. We won't dive too deeply into reinforcement learning. It's kind of a niche specialized field, but supervised and unsupervised, we'll talk about later in this presentation. So just to give you some insight into reinforcement learning, it's just a way to learn from an agent and learn from an environment so that we can learn things through trial and error and just be able to converge to an optimal solution. Oftentimes, one good example of where reinforcement learning makes sense is when it comes to video games. In a video game, it's the same state, it's the same model every single time. It's the same rules. There isn't a lot of uncertainty. So when you do reinforcement learning, we're able to just keep on repeating and repeating a game, for example, and be able to learn from our mistakes and optimize our process. There have been reinforcement learning used in a lot of different games. For example, chess uses reinforcement learning, though it does use some other machine learning ideas like Q-learning. Games like Tetris, games like Pac-Man, you can use reinforcement learning to kind of optimize things. And the reason why reinforcement learning works really well with games is the idea with reinforcement learning is there's a set of states, actions, and rewards. We want to find a way to maximize the reward. So states and actions map really well to video games just because of the nature of the game. For example, an example of a state would be like a chessboard or a specific configuration of pieces. Or the example of a state in Tetris would be a board state. An action would simply be like, I move this queen to square A5, or I move my Tetris piece one shift to the right or one shift to the left. And the reward would have to be some form of value dependent either on the game itself or some abstraction of the game. For example, a reward in chess could be some type of way to know, hey, this board position is really good, or I have more pieces than my opponent, so I have a greater reward. So this action I would take would give me a greater reward. Or when it comes to Tetris, you can base it off the score, or how close you are to ending the game, or how many pieces are in the board right now. So this is all very general, but the key idea behind reinforcement learning is we don't know a reward and we don't know a model, so we just learn through trial and error. So we just repeat action, we observe the state, the new state, we look at the reward, and we just repeat this process a lot to get idea. And the main idea here is we just do a lot of trial and error and are able to learn from our conclusions. However, reinforcement learning isn't too relevant, and it probably won't be relevant for most machine learning use cases. For most machine learning use cases, we can divide things down into supervised learning and unsupervised learning. So it's kind of important to understand the nature in which we get data. So data could be pre-labeled or it could have no labels at all. For example, if you just get a bunch of raw data, like the example in the unsupervised learning, we have no idea about what the data is or what it belongs to or anything about the data at all. We just have a bunch of features which we represent here in a graph with X and Y values. And when we're dealing with unsupervised learning, we have none of the label data. However, when it comes to supervised learning, we have some of the data when it comes to the labels. You can see just in the image, I feel like a good way to describe this is just through images, is that when it comes to supervised learning, we have access to knowing, hey, this data point is red or this data point is blue. When it comes to unsupervised learning, we have none of that information. So supervised learning has label training data where unsupervised learning does not. So here's an example of what an actual data set would look like. We have a bunch of points. We have, these are just like entries or data points. And then we have our features, which is the weight, the height, the fur color, and the eye color. And then if we were dealing with unsupervised learning, we have none of this label training data. This label training data on whether this data point refers to a cat or dog doesn't exist. But if you're dealing with supervised learning, this label data point does exist. Essentially, unsupervised learning, we only have this X data. When it comes to supervised learning, we have both the X data and the Y data. And this is really important because you're not going to always have these labels. The big power of supervised learning is that we have these labels and we have this data. So what can we learn about the labels so that we can predict new labels without knowing the previous information? So unsupervised learning, we don't have these labels. Supervised learning, we do have these labels. So some of you might be thinking that we don't have these labels, we just have a bunch of raw data. What can we actually accomplish here? So even if we don't have information on the data labels, we can still perform analysis and we can still learn a lot about the data set. And some algorithms here that are really powerful are clustering and dimensionality reduction. So when it comes to clustering, we just want to see that this data looks like this other piece of data. So we can see that they're kind of similar. And dimensionality reduction is saying this feature isn't necessary. It can kind of be transformed. So let's dive deeper into what clustering and dimensionality reduction actually look like. And for both of these different techniques, there are numerous amount of algorithms. There's tons of research. Each of these could be an entire course on itself. So here's kind of a big, kind of like an overview of what clustering looks like. For example, we have this raw data, which could be represented as an XY point in a graph. We want to cluster data points together. There are a ton of different algorithms. Just like you can see 16 of the different algorithms that are used here. There's a lot of different ways to do clustering, and that's because it's a very hard problem. How do I know that this data point looks like another data point? It's a very hard thing to know, especially when all we're dealing with is X and Y data points or just a bunch of different features. So clustering doesn't have to be done with just integers or numbers. It can also be done with images, as we can see here. It's very important to remember that when we're dealing with images, when we're dealing with computer vision, an image is literally just a collection of pixels, and a pixel is just a bunch of numbers. So each pixel is just a red, green, and blue value ranging from 0 to 255. So when we take this image, we can cluster it based on intensity, we can cluster it based on color by transforming the image to a bunch of integer data points. And then once we run our algorithm, we can transform it back to an image just to get information. So I just thought this was a pretty cool use case of how we can use clustering on things that are not raw numbers or raw data. So let's take a look at k-means, which is a pretty standard and pretty classical clustering algorithm. So we have a bunch of data, which we represent as an XY point, and we have these kind of randomly generated points. So as we can see, the white points are unsupervised data. We have no information. White points, which are kind of unsupervised data, we have no information on them. And then we also have these cluster points, which can be defined here as these X's we see here with this green X, this red X, and this yellow X. And we just randomly choose a bunch of cluster centers. From there, we calculate the distance from the cluster center to all the nearby points, and then we assign each point to the nearest cluster center. We can kind of see that here, and it makes sense in this case because we're just dealing with distance. So it's kind of intuitive to see that each point, we just map it to its closest cluster center. From there, what we can do is we can readjust the cluster centers and take the average. So the key idea here is that we have data points and we're trying to find the cluster center that corresponds to all of these data points. So describing this algorithm out in words and in steps, we get this following idea. First, we want to initialize some number of centers randomly. In this case, let's just say we initialize k clusters. From there, we assign the data points to a cluster. And this can be done in a various number of ways. Usually we use a function, and most of the time we just base it off distance. This is just like our standard distance function, like x squared plus the square root of x squared plus y squared to get a z value, mapping the two values together. And then once we assign each data point to a cluster via a function, which is usually a distance, we readjust the cluster centers to try and converge to a solution. So when we readjust the cluster centers, oftentimes we just take the average of all the nearby data points, and we just repeat this process until we reach a stopping condition. So the stopping condition in analysis algorithms can vary a lot. So sometimes we just run it for, let's say, 100 iterations. Sometimes we run it until none of the data points swap between clusters. Sometimes we run it for like 10 minutes, and then after 10 minutes, we just have to move on. So the stopping condition is something that's defined by you yourself, the software engineer. So k-means has a few pros and cons, and it's a really classical algorithm, which means it has all these things have been analyzed pretty well. So some of the pros of k-means is that it's pretty simple to implement, it's pretty simple to understand, and it works. Oftentimes when we're dealing with data that is close together is data that is similar to each other. So it's pretty simple to implement, it works, and it's guaranteed to converge to a solution with enough iterations. So if we run this code enough times, we'll be able to get a solution. In addition, it generalizes clustering to higher dimensions. So one thing to keep in mind when we're dealing with data, when we're dealing with features, is there's a lot of data, there's a lot of features. So for example, for this data set, all we have now to map this data is an X point and a Y point. But when we're dealing with a big data set with a bunch of different features, we're not just going to have an X point and a Y point. We're going to have an X point, a Y point, a Z point, and so many more dimensions to our data set. So we want to make sure any clustering algorithm we use generalizes to a higher data set. However, there are a few pretty big cons when it comes to k-means. And the biggest one is to know how many clusters we're choosing. You remember at the start when describing this algorithm, I said that we initialize these clusters randomly. And that's kind of dangerous because we don't know how many cluster centers to initialize. So picking the number of clusters to initialize is a pretty difficult problem. In addition, the amount of time it takes for this algorithm to run is pretty dependent on our initial values for the clusters. And usually we randomize things, but it could take a very long time to run if our randomization is bad. In addition, when we're dealing with outliers and when we're dealing with like high dimensions and we're dealing with like 10, 20 dimensions, and computing distance now requires computing distance over 10, 20 different dimensions, it becomes a lot more complicated. In addition, k-means does a pretty bad job at clustering certain types of data. So usually it works because usually data points that are close together are similar, but we can see that there are a few instances with certain types of data where k-means doesn't really work. For example, some of the issues when it comes to choosing the number of clusters can be seen in this image. So we have some data points and we have the labels just to understand how the clustering works. But if we only choose 2 clusters, then we'll be making some mistakes when it comes to clustering. If we choose 5 clusters, then we'll be combining this red and blue cluster together into one big cluster. So knowing the value for k and knowing the number of clusters we choose is a pretty big problem. And there are a few techniques to get a good k value, but that's one of the big downsides in k-means is we don't know how many clusters there are before running the algorithm or before running some other algorithms to get some insight. So the big algorithm or the big insight when it comes to finding the number of clusters is to use this elbow method. And this graph is very like abstract. We don't even have a y-axis label. But the key idea here is that after a certain number of clusters, the error will decrease drastically. So we can see that if you have 2 clusters, we're pretty far off and there's a pretty big error. If you have 5 clusters, there's still a pretty big error. But after 6 clusters, the error kind of levels off. Like we're pretty close to the actual data with 6 clusters. So the idea here is that we run k-means a lot of different times with a lot of different clusters, and we just find which one has a loss that starts leveling off. So we see here for this example that once we get to 3 clusters, then the error kind of like doesn't really move too much. And then we know that 3 clusters is a pretty good approximation of our data. Here's an example of a data set where k-means doesn't really make sense. So we see that k-means what it does is just uses a distance function. So some of these points would be mapped to each other, but k-means would do a terrible job on this data because we just base it on how close the data is. However, as a human, we can kind of see that, oh, it's like a spiral pattern, and this orange data obviously kind of maps to each other because it just kind of looks like a spiral. It's a contiguous spiral, but k-means will just take the average of the distance, and there'll be a lot of error if you use k-means for this data set. There are a few different other clustering algorithms. You can kind of see some of them in this animation here, but we're not going to dive too deep into them. Just be aware that these are some clustering algorithms that could prove helpful. So mean shift clustering is kind of similar to k-means. We just take the mean of a bunch of data and then we shift our data points. DB scan is what you see here with the red dots and kind of like the expansion of the clustering algorithm. So DB scan is really good when we're dealing with noisy data. And what it does is it just looks at data and finds nearby data. And then when we can no longer find nearby data, we just start a new cluster. So it's kind of encapsulated in this animation. We get a pretty good, I feel, idea of how DB scan works from a visual aspect. It also does a pretty good job of dealing with outliers because it doesn't assign outliers to any clusters, where k-means will assign every single data point to a cluster. GBS-scan does a kind of good job at dealing with outliers and dealing with noise. The Gaussian mixture model just deals with Gaussians, and it's a different way to cluster data instead of using distance. And then hierarchical clustering is a way to cluster data, and it works really well when we're dealing with when we could have a possible number of clusters. So we can kind of see that in the animation on the right, where we cluster things together based off how close they are. We can kind of see this dendrogram, which maps things out and says this data is kind of similar to this data, and we can combine clusters together. Starting out, so the thing with hierarchical clustering is at first, we assign each data point to its own cluster, and then we slowly build up and combine clusters together hierarchically, which we can kind of see through the animation. Dimensionality reduction is another pretty big idea when it comes to analysis. So don't confuse dimensionality reduction with like feature reduction or feature removal or data augmentation. Dimensionality reduction is an actual algorithm that's used when it comes to analyzing data. And it's really important because it helps us know how well two features are correlated. For example, if you're dealing with a data set where there's height and weight, oftentimes height and weight is correlated to each other. But if we're dealing with a data set when we're dealing with, let's say, ethnicity and let's say height, there is, I guess, some correlation there, but not as much as it is with height and width. So dimensionality reduction is a good way of understanding what features are actually important, what features vary more than other features, and what data and what features are correlated with each other. And some of the techniques here are PCA and SVD. And this image gives us a good idea of how when we're dividing up this class, a lot of the data varies in this line, while the data in this kind of this line here doesn't really vary too much. So we see that this axis is much more important when it comes to deciding what data point belongs to which class, whereas this axis, like from left to right, is not too important. So the key idea with the principal component analysis is that we sort the features in importance of how much they vary. So if some features vary a lot from each other, then we know that, hey, that's a pretty big sign that something's important. And then we just disregard dimensions that aren't really too important. We can kind of see in this drawing that x3 is not too important. This data set kind of lies mostly in x1 and x2, and there isn't much variation when it comes to this additional dimension. So we just kind of remove it, and then we transform our data. We see that the maximum variance is across this x2/p1 data set. So we can just reduce the amount of dimensionality when it comes to that. And this has some really cool applications. Knowing that some features in the data set is not important and knowing that some features in the data is important, and transforming our data has a lot of cool ideas and can have a lot of cool project-based applications. For example, image compression can be done using PCA. We just know what portions of the image is important, what portions of the image is not important, and then we can just reduce the image. We can kind of see that here when it comes to this image of this owl, that when we don't have any removal, then we see that we have a pretty clear image. But as we remove some of the principal components, and as we reduce the amount of variance, we get a slightly more and more compressed image. And this can just be done by taking the image, converting it to values with integers and floats and doubles, and then just compressing it by removing the amount of variation when it comes to the image itself. So that was some of the ideas when it comes to unsupervised learning. There's a lot more algorithms, there's a lot more techniques, which we'll dive deeper into in future workshops. But now let's switch to talking about supervised learning. So the big thing when it comes to this unsupervised learning is we see that there's no labels when it comes to the data. We don't know whether this data point belongs to a label cat or a label dog. When it comes to the hierarchical clustering, we just have points in space. We don't really know prior to running our algorithm whether or not it belongs to a specific label or not. So the idea with supervised learning is that we do have this information. We do know that this data point belongs to this class beforehand and before running our algorithm. And this leads to some more possible algorithms, and this leads to a lot more that can be done when it comes to our data set. So we can see here that this unsupervised learning, that we don't have a lot of information, but we can say that this data is similar to this data. We can cluster the data. When it comes to supervised learning, we can actually do a lot more. For example, here, we're dividing the two data points together. So one big idea with supervised learning is that we can actually test our results. So with unsupervised learning, we don't know whether or not a data point belongs to a specific label or not. But with supervised learning, we can actually test our results. We can use training and test data and we can split our data up and say, hey, this is our algorithm, and let's see if it actually works. And the way that we do this is by splitting our data into chunks. So some big problem when it comes to splitting our data is with overfitting, which we'll get into a bit. But I think it's more important to first talk about this training test data split. So first we start out with our entire data set, and we use training to train our model, to find parameters, to kind of like find all these important insights when it comes to the data. Then it's kind of important to test our data. So we just divide our data set into randomly into a training portion, which we actually train our model, or testing portion, where we see, hey, does our model work when we're dealing with new data? And it's really important to have this testing data set because we don't want to overgeneralize to our training data. And then oftentimes in actual practice, we'll have a validation data set too. This isn't too important, but we just want to make sure that we find our happy parameters, which we'll get into a bit later. But what I really want to hammer home when it comes to this slide is that we need a test to make sure that our analysis tools are actually working. And the best way to do this is to divide our data set into a training and test data split. And when it comes to our training and test data split, the reason we want to do this is we want to make sure we don't overfit to our data. When it comes to analysis, we are very much limited by our data set. If we don't have a lot of data, then we can only learn what's in our data set, and we want to make sure we have a general enough model. So there's a few risks when it comes to analysis models, and this is kind of universal when it comes to analysis and with supervised learning. These are problems that exist when we're dealing with regression, or we're dealing with estimating lines, or we're dealing with neural networks, or we're dealing with like any form of analysis has these problems where we want to get a good fit, but there are some issues that can arise. For example, we see that if we don't have enough complexity, then we underfit our data. We see that this dividing line here does a really bad job of matching up to our data values. It like does not capture any of the complexity, does not capture the actual data set. However, if we have a good fit, then we see that, oh, we captured the general trend of the data points. We do a pretty good job of matching up to data, even though we see that, oh, like the line doesn't exactly match up with the data. It captures the general trend, which is what's really important, is that we want to capture the general trend without overspecifying, without overfitting to our data. And we see this here with our overfitted data set. It kind of makes sense that like, hey, if we're just like going like very, very close to our data and we're just like manipulating things to where we match up exactly to our data, we aren't really capturing the general trend of the data. We're just hyper-specifying and we're overfitting to our data, which while it does look good and while like, oh, we can see, oh, it matches up with the data, there isn't much of an error, like it's really close to the data, this would perform terribly when it comes to new data because our graph doesn't really capture the general trend of the data. So we can kind of see that here in this green and blue, red and blue graph, where if we overfit the data, then we have this very green jagged line which curves back and forth and curves back and forth and just doesn't really capture the really key insight, which is captured by this black line. And where this black line gives us a general trend and gives us a general boundary line for the data, this green line just overspecifies and it overfits and just will do a bad job when it comes to predicting future data. So now let's talk about parameters and hyperparameters. We'll dive deeper into this when we deal with neural networks in our next workshop. But the idea here is that hyperparameters are kind of like systemic, kind of like general ideas, and they're parameters related to the model, where the parameters themselves are like variables related to the model. So the way I describe this is that hyperparameters are tunable aspects of the algorithm. Like how many times are we running this algorithm? How many iterations? And a really good example of this is the number of clusters in k-means. Like that's not, the number of clusters in k-means isn't related to the data at all. It's related to our model, where the parameters are related to the data itself. So some examples of hyperparameters are the number of clusters, how many iterations, the architecture of our model, our learning rate, where the parameters are actually related to the model itself, and they're kind of like specific to the model we use. For example, we see here that we have this graph which divides into data sets. The equation for this black line would be a parameter. We'd have y equals mx plus b, or in this case, it'd be something like y equals mx squared plus cx plus b. So those variables, M and C and B, are our parameters. So as I described here, if we're trying to predict a line, then M and B are the parameters, and they are very specific to the model, whereas the hyperparameters would be something like more general to the model itself. Uh, we'll dive deeper into this with our neural network workshop, but just some ideas that like the actual values inside the neural network are the weights, whereas the hyperparameters are stuff like our learning rate. It's stuff like how long do we run the neural network for. These are kind of more general problems with the model. So now let's talk about some supervised learning algorithms. So as mentioned before, supervised learning, we have information about the label, which makes it really easy to predict new data. For example, if we have some data points like plus signs, some data points like minus signs, we can just graph a line dividing the two data points from each other. We can see, hey, if our new data point is up here, like in the plus section, then we'll say it's probably a plus sign. If our data point is down here in the minus section, we can say, hey, it's probably a minus sign. So predicting some of the values can be really easy if we get a linear classifier. Essentially, a linear classifier is just a way to separate data from each other, and it's a separating hyperplane between a binary class of data. So one thing I'm doing in this workshop, and what you'll see in most machine learning classes, is that for the purpose of learning, is we're dealing with graphs with two data sets or two data points or two features. But when we're dealing with actual machine learning projects, when we're dealing with actual real world problems, there's going to be a lot more dimensions to this problem. We're not just going to have an X value and a Y value. We're going to have an X value, a Y value, a Z value, an information on hair color. We're going to have information on just a lot more features. So for the purpose of this, for the purpose of teaching and for the purpose of this graph, we're dealing with 2 points. Just know that all of these ideas can be generalized up to higher dimensions. So we see here that it's just a line separating the two data, but if there's an additional dimension, all we have to do is add a plane. And if it's more than three features, then things generalize to a hyperplane. And there's a lot of math that goes into that, but usually all of the machine learning libraries will have information when it comes to how to implement this. Like these, you will never have to calculate this line by yourself. Every single machine learning library will have a way to automatically calculate this, or they'll have a way to set things up to where it'll be very easy to find the equation of this line. And then if the data is linearly separable, and if things fit into these like neat bunches of minus signs and plus signs, then perceptron is an algorithm that will divide these two data points from each other. So the problem with perceptron is we see that, hey, there's this line that divides the data, but we can make lots of lines that divide the data. So what is the best line that divides these two data points from each other? That's where we talk about support vector machines. So the idea with support vector machines is that there's lots of different lines, like one line here, one line here, one line here, that separates the data. So what separating line would give us the best prediction? And the idea here is that we just want to pick the separating line that gives us the biggest margin between the minus sign and the plus sign. So if we predict like this separating line, like this one that's very close to minus signs, then we see that this is not really a good separating line because it doesn't give us a lot of margin of error. Whereas this line gives us a big margin of error. We can say that, hey, if it's like below this dotted line, it's probably a minus. If it's above this dotted line, it's probably a plus. And if it's in this area, it's like we're not as confident about it, but we can still make a general prediction. So the support vector machine is just a more specialized version of perceptron, which does a better job of dividing these two data points from each other. So one big idea when it comes to supervised learning is classification versus regression. When we're dealing with supervised learning, our labels could vary a lot. So sometimes our labels are, like as mentioned at the very start, sometimes our labels are information like cat and dog, but our labels could also be values. So when we're dealing with regression versus classification, what we're really dealing with is predicting a categorical value versus a numerical value. Regression involves predicting an integer or like a double value or like an actual number, whereas classification, we're just dividing between a few different labels. So all these examples we've done so far have been classification. We're predicting dog versus cat, or predicting red versus blue, or predicting minus versus plus. Whereas regression will be a lot more complicated because what we're actually dealing with numbers. We have to predict a a value. So the example I gave here is when we have a square footage of a house, how can we predict its price? And what we can do is we have a bunch of data points. We can predict a regression line, a line of best fit. But there's a lot more that goes into regression than it does classification. And there's a lot more that goes into classification as well. But for the purpose of this workshop, I feel like I've done a good job of giving an overview of the different machine learning techniques and the different aspects of machine learning. So the key things to keep in mind are that we want to deal with data. So there are a few tools that come into play. We want to make sure our data is clean. We want to make sure our data is organized. We want to make sure our data is ready for our analysis, because if we put garbage data into our analysis, we're going to get garbage data out of our analysis. Then when we're dealing with our actual analysis portion, we can have unsupervised or supervised data. So unsupervised data is when we don't have information about the labels, and supervised data is when we actually do have information about the labels. And based on that, there are a few different techniques we can use. Just for the purpose of time, this concludes this workshop. We'll dive deeper into some of these concepts in the next workshops. So look forward to next week, next Tuesday, when we dive in deeper into neural networks. And then I hope to see you all this Thursday at our workshop. We'll be going through an interactive example about learning more about analysis, learning more about data cleaning, and learning more about regression and clustering. So this concludes the workshop. Here are a few different links to resources that could be pretty helpful. So if you don't have too much experience with Python and NumPy, here's a Colab notebook, which will walk you through some basic Python syntax, some basic NumPy syntax, and how you would actually use that. If you want to understand how machine learning models actually work and kind of do some self-learning when it comes to that, here's a link to a pretty important and pretty useful Kaggle tutorial, which goes through machine learning models. And then oftentimes when you're working on your projects, you're going to have to use like software like GitHub and like Git. So if you don't know how to use Git, then here's a specific tutorial which goes through learning how to use GitHub. So this kind of concludes our workshop. And if you have any questions, or if you want to just learn more about any of these topics, feel free to reach out to me and I'll set you up with the right resources to learn more. Thank you.